and get set up from the current slide. Okay. Now, that was from before. Okay, where I have my mark was page 667. Is that about okay? Just finished example 4. Haven't gotten to example 5, right? Okay. This figure that we have here was from a previous one, but I think this is one we're writing on now. But before we get there, this definition, I don't think we did this one. The intersection of a plane, this is the P-plane, that sort of a script-looking P, with a coordinate plane. Now, what do we mean by a coordinate plane? Okay, yeah. Say, if this is the plane P, which is labeled as, its intersection with the coordinate plane, there's 3 coordinate planes here in 3 dimensions. There's the XY plane, the YZ plane, and the XZ plane. Those are the coordinate planes. So the intersection of this plane with the XY coordinate plane would be some line that goes, looks like if you extend this on down here, it would be a line that is something like this. Okay? And that's where it would intersect that plane. The YZ plane, I can't tell here where this is. If it's standing out here or back there, but it would be some line that went up like that, perhaps. And the XZ plane, probably something that went across like this. Okay, so those would be the intersections of a plane P, a generic plane with a coordinate plane, or a plane parallel to a coordinate plane. So let's say we had this coordinate plane, the XY coordinate plane, is where, of course, Z is equal to 0. But you could come up and say it's Z equals 7. That would be, but that would be a plane parallel to the XY plane, but over here Z is 7. That would cut across this plane at a certain place. Those things like that are called traces. Okay? The intersection of a plane P with a coordinate plane or a plane parallel to the coordinate plane is called the trace. The trace is a line unless P is parallel to a coordinate plane, in which case the trace is empty or it's a whole plane. Okay, because of course if that plane was parallel to the XZ plane, XY plane say, but not on the XY plane, then it would be no intersection. Or if it happened to be the level where it is parallel, then the whole plane would be that trace. Okay. So with that in mind, we're going to this one. This is, it says graph on the plane. Now graph the plane minus 2xy, and here it is. I'll blow this up for now, but it's not going to be any time much before I'm going to have to shrink it back down to write on it. Okay, but here it is. Here is the plane, minus 2x plus 3y plus z is equal to 6. That is a plane in 3 space. Minus 2xy plus 3, 2x plus 3y plus z equals 6, Okay. Now, graph the plane, then find its traces on the coordinate planes. Wrong order. Okay. Far easier than to try to graph it first. Pick out the places that make sense for you first. Okay? And what makes sense to me is, say x and z is 0. Where are you then? X, z, 0, y0 and z is equal to 0. So y is equal to 0, you're on the xz plane. and z is equal to 0, that's the only place that it crosses the x-axis, okay? Well, when you set those equal 0, minus 2x equals 6, x equals negative 3. There you are. That's where it crosses the x-axis, okay, when you're on the YZ plane. Yeah, on the YZ plane. So here's the YZ plane here. That's the west. So y is equal to 0. Yeah. That's the one place it crosses. When x equals, y is equal to 0, x equals, z is equal to 0, x is equal to negative 3. Do it this way, where x equals 0, y is equal to 0, z is equal to 6. There it is. That's where it crosses the z-axis. Yeah, because on the x-axis, y is equal to 0 and z is equal to 0. On the z-axis, x is equal to 0, y is equal to 0. And the one we haven't got done yet, is, yeah, y. These, okay. These two equal to 0, then y is equal to 2. There it is. Okay? That gives you 3 points right there. And basically, those 3 points then graph the thing for you. Okay? Except that those 3 points also, if you connect the place where on the x-axis and z-axis, you just define the trace on the xz plane. Okay? And then when y, it crosses the y-axis and x-axis, you've defined the trace, the one line on the xy plane. And then also the y is equal to 2, z is equal to 6. That's the point there. Now, what we haven't done is written them as an equation, so you can do that as easily. And guess what? Let's take that first one that I said, z, x, the xz, put y is equal to 0, and there you have it. Minus 2x plus z is equal to 6. There it is. That's the line, yeah. And do that on all 3 of them. So, pretty easy process to do. Find those points first. Now, this one's really easy because all 3 of these coefficients go into that even number of times. I mean, a whole number of times. So that was really easy to pick out. If this had been minus 7x plus 13y plus 21z is equal to 17 halves. Yeah, that's going to be a mess, but it's going to be a mess no whatever. So, yeah, you've got it. Okay? So the 3 blue lines are the traces of the plane in the coordinate planes. Okay? Okay, say that one more time.
If you connect the 3 trace lines, does that make the plane, or does it make a plane parallel?
Okay, those are all on this plane. Yeah, they're all on this plane because those 3 points are on the plane, and any line connecting the 2 points are on the plane. And there isn't a line that connects all 3, but the 3 lines that connect all 3, they're on the plane. So then you just sort of, it's so hard to draw these things, 3-dimensional thing in 2-dimensional board, you know, it's just hard to do, but you get the general idea. Now, what I should have done to begin with, they oriented this plane a little strangely. There goes x this way, y's this way, and z's up. So yeah, you got a right-hand system, but this isn't how we usually orient it, but they just twisted it around here so you could see better how this works. Obviously, you're on negative x here, the positive y, that's kind of coming out of the board here. And z is the only one that's sort of in the right place, is going up. X is kind of coming out of the board, but not nearly as much as y is, you know. And so this one is actually back there behind the board a little ways. So it's really hard to get, but yeah, that then defines the plane. getting it to look like it does is maybe a different story. Okay. So, to me, they do it right. Yeah, they found first the 3 points, then connect any 2 of the points will form the trace, and then you don't have to really do much to come up with the equation for that. You just wipe out the one that's missing, and you've got the exact one you need. All right, so that's a pretty simple process. So that was 12.5. Any questions? I don't think there's any other, any other thing here. Do you want to do the preliminary questions, or do you find, okay, do those. What is the equation of the plane parallel to this one? Oops, let me get my pen activated. I'm trying to activate, there it goes. Okay. What is the equation of a plane parallel to, so it's parallel to 3x plus 4y minus z is equal to 5. Okay? That passes through the origin. Okay? Obviously that picture doesn't apply to here. The plane that's parallel to that plane that passes through the origin. Any guesses? Okay. A little bit of a review type thing. What do these coefficients, this is minus 1 here, 3, 4, and minus 1, what do those represent? If it's not represent, what do they correlate to? What were you saying? Yeah, the normal vector. Okay. Now, if you're looking for a plane that's parallel to that plane, guess what? Same normal vector, right? Got to be, if it's going to be parallel. Okay. So if it's the same normal vector, your coefficients are exactly the same. If it passes through the origin, guess what the constant's got to be? 0. Yeah. So that's it. That's it. The one that should be it exactly. Okay. Let's make sure they don't do anything else strange with it. 12.5 preliminary question. 3x plus 4y minus z is equals 0. Exactly. Okay. Number 2. I think since I don't have a lot of room to write, I'm going to erase that one and use that top space again. The vector k. What can you tell me about the vector k? Feature of it. 2 things you can tell me about any vector. Okay, what's its magnitude? One. It's a unit vector. When you see I, j, or k, they don't use those for anything else except the unit vectors, and it's in the direction of the positive z, usually. I mean, that's how we do it. Okay. So there's the vector k. Is normal to which of the following planes? Is normal to which of the following planes? X equal 1, y equal 1, or z equal 1? Is normal to which of those planes?
So you said k is equal to, k represents the z-axis.
Yeah, it's 1 unit up the z-axis, wherever it happens to be.
And to be normal means to be orthogonal to the...
Marcus is here. Say that again.
To be normal means to be orthogonal to
Right.
So couldn't it be x and 1?
Okay. Except now, here's the thing. The plane at x equal 1. Okay, let's just imagine there's my x-axis, there's my y-axis, here's my z-axis. X equal 1 would be this plane right here. Ooh, what is this? Oh, just a mark on the floor. Is the plane here. And the k is not. It's yeah. Yeah.
It would be C.
Second?
C.
C? Yes, meaning Z. Okay, meaning yes in Spanish. Yes, I got it. Okay. Yeah, it would be C, which is Z is equal to 1. Okay? Orthogonal to that. Okay? Anywhere that plane Z equal or K would be orthogonal to Z equal any constant. Exactly. All right. Number 3. Again, I think I'll just have the most white space available. Let's do 3. Which of the following planes is not parallel to this plane? X plus Y. We're on the preliminary questions and 2.5 exercises on page 668. Okay. I figured you already had it. I forgot to say it. Okay. I lost it now. Plus Z is equal to 1. Okay. Which of the following planes is not parallel to that plane? Here are the choices. 2x plus 2y plus 2z is equal to 1. X plus y plus z is equal to 3. And x minus y plus z is equal to 0. Which one or ones of those is not parallel to the one given at the top? And Silva. Okay. 3 out of 4 are here. Only missing Faith. Second? Okay, you're still going with yes again. Okay. You're absolutely right. Okay. We're doing the page 668, chapter 12, section 12.5, preliminary questions. And we've just done the first 3. So here's number 4. Okay, and I'm going to, because I don't have much white space on this one, I'm erasing them all. I'm trying to anyway. To which coordinate plane is the plane y equal 1 parallel? To which coordinate plane? Whoops, I put perpendicular. Okay. Is that plane parallel? Second? The XZ plane. You're absolutely right. Okay? The XZ plane. Okay? Just making sure that the back of the book is agreeing with us. Well, I had it. There it is. C, FC plane. Right. Okay? Number 5. Which of the following, I think I'll erase this again. Okay? Which of the following planes contains the z-axis? A, z is equal to 1. B, x plus y is equal to 1. Okay? Or C, x plus y is equal to 0. Okay. Which of the following planes contains the z-axis? Z is equal to 1, x plus y is equal to 1, or x plus y is equal to 0. C again? Okay. That sure seems like it fits to me, because x plus y equals 0. Here's your xy plane, and if x plus y is equal to 0, that would be a line that actually would be this diagonal here. The off diagonal So if you got a minus x or a plus y, that would equal 0, or plus x and minus y would equal 0. Along the same thing. And the z axis would be on that. No matter what, where x is equal to 0, y is equal to 0, z is equal to 0 too. I mean, x plus y, so the plane that would contain the z-axis, because everywhere on the z-axis, x is 0 and y is 0, so sure, that would be it. Z is equal to 1 would be a plane. The z-axis would be perpendicular to z is equal to 1, so it couldn't be that. And x plus y is equal to 1, then that would be the line that goes across here from plus 1 to minus, plus 1 here, plus 1 on y. That line that goes like this, then z-axis would be anywhere on that. Okay. Everybody concur? So it seems like they're really liking C answers, aren't they? C, C, C. Okay. How about number 6? I'll tell you ahead of time the answer is not C. Okay. Now, suppose, let's go on and wipe this out. Tells me you can't put 4 C's in a row. Okay. Suppose that a plane P with a normal vector N and a line L with direction vector V both pass through the origin. Both the plane and the P pass through the origin, and that N dot V is equal to 0. What in the world does it mean for N dot V to be equal to 0? What can you tell about N and V then? If the dot product is 0. They're what? They're parallel to each other. You're absolutely, no, not parallel, I'm sorry. Perpendicular to each other, sorry. They're perpendicular to each other. Okay? So, so we have a plane. Let's use the one that's here. No, we can't use the one that's here because that doesn't go through the origin. Okay? Let's see if we can find one that does. No. All right. Now, this plane right here goes through the origin. Okay, this one doesn't. It goes through plus 12. This one down here doesn't. It goes through negative 5. But this one right here goes through the origin. 7x minus 4y plus 2z is equal to 0. It doesn't have to be that. That one goes through the origin. Okay, because x equals 0, y equals 0, z equals 0. We make that have to be 0. Okay. So that one goes to the origin. Okay. So here's a plane, and it has a normal vector, N, and a line L with a direction vector V, and both of those two pass through the origin. The normal vector does, and the direction vector both pass through the origin. Now, give me the normal vector for this plane here, the one that we know goes through the origin. What's that? Yeah, it'll be perpendicular to this, and since I can't really tell what direction this is, somewhere like this, it'll be pointing somewhere like that. But can you give me that normal vector? Earlier. That's the equation of the plane. What's its normal vector? The coordinates, yeah. So the normal vector to that thing, okay, I'm sorry. I made it a unit vector and it's not. But the normal vector to this plane here would be 7 minus 4, 2. Obviously not a unit vector. Okay. Now that's just this one. This doesn't have to be, but that's your normal vector. Something coming out of the board this way. Okay. Okay. So this plane with that normal vector n and the line with the direction vector v both pass through the origin. The plane and the vector. So the line passes through the origin, and I don't want to write anything else on here yet, I don't think. Okay. Pass through the origin, and n dot v is equal to 0, means they're perpendicular to each other. Which of the following statements is correct? First, A is L contained in P, B, L, whatever you say that, is perpendicular, orthogonal to P. Which of, oh, I didn't realize they have a unit vector here. There it is. Okay. That's of that one, but it's also the same unit vector of the one down here that we were dealing with. It doesn't have to be there, it can be anywhere there on that point. Okay? So, which of these has to be true? H? Oh, A, okay, yeah. I was going to say, all right, he's thinking deeply here. All right, yeah, A has to be true. Because for the direction vector in L to be perpendicular to this N, it has no choice but to be in that plane. No choice at all. There's no line perpendicular to that vector V here that's not in that plane. So yeah, it has to be contained in P. So I told you that wasn't C. Okay, I gave too much away there, I'm sure. Okay, yeah, statement A. Good for them. Homework exercises here. I've given most of these before, but in case you didn't get them, any of the odds 1 through 7. Do either 9 or 11 or both, either 13 or 15 or both, 17 or 19 or both, any of the odds 21 to 27. Do 29, it's the only one like that. Any of the odds 31, sorry, to 35. Do 37, okay? Either 39 or 41, or both. Any of the odds 43 to 47. Any of the odds 49 through 53. Any of the odds 55 through 59. And any of the odds 61 to 69. Okay? Any questions on 12.5? Okay?
On that last one?
Yeah.
We couldn't assume that it was in the plane, but we know it is because of the origin, because they said that both of them are at the origin. Is that right?
Okay. I see. Your question, did they have to both of those go through the origin?
No, because it says that they both go through the origin. If it didn't say that, then we couldn't assume that they were in the same plane.
Right. Yeah. Let's just imagine that vector, what you see here, this n, that's not in this one, but then any vector in this one, okay, even that went through the origin or not, well, yeah, any vector in this plane, those are So, let's see, how to phrase this. By requiring both of them to go to the origin requires them to have one point in common, okay? Whereas this normal vector here and some vector over here, they're also orthogonal to each other. If you did the dot product, they're zero, but they never cross, okay? So just having the other two conditions, that this is the dot product of these two vectors is zero, just means they're going in a direction that, like this one would be here and this one would be anywhere in this plane. Those are obviously perpendicular to each other because any vector in this plane is parallel to a vector in this plane, and that would be perpendicular to the normal. So, yeah, you have to require to have some point in common for them to be in the same plane, and that is what is either contained in the plane perpendicular to the plane, and for them to be in the same plane, they have to have a point in common. So they picked the origin. It didn't have to be the origin, but they had to have some point in common. Yeah, and it was just an easy one to do. So, does that answer what you're asking? Yeah. Okay. Yeah. Good thought on it. Okay. Now, this is where I need a little timeout. Sorry, folks. I had meant to do this last week, but I got hit, I guess is the best way to say it, with a requirement last week that just threw my whole week off. And I didn't get this done, and then I didn't take home enough stuff to do it there. I'm going to need just a moment. So what I'm going to do is pause right here,